Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE314 Measurements and Instrumentation. This is the second lecture of your online lecture series, lecture number 26. And in this lecture, we will continue with the operational amplifiers and its different configurations. So now let's move on to the summing amplifier. Now, what is a summing amplifier? It is a modified form of an inverting amplifier. So let's draw that. If it is an inverting amplifier, let's put a ground to the positive terminal. And if it is a summing amplifier, we will be doing sum of two or more than two voltages, right? So there would be at least two inputs to this configuration. I am using three inputs. So let's do it like this: V1, V2 and V3. And this is R1, R2 and R3. And here, just like before, we will connect a feedback resistor, that is RF. And at the output, we are getting our output voltage. Now let's try to find out the relationship between this V out and these multiple V ins that we are providing. What we can do is we can solve for this V out for these individual V ins and then use the superposition method to find the final V out with the combined expression of the V1, V2 and V3. So let's use superposition method and let's assume that one by one we will solve for V out, for V1 and then for V2 and then for V3. So when solving for V1, we will assume that V2 and V3 are equal to 0. So let's start. V1 is equal to V in and V2 is equal to V3 is equal to 0. Now when V2 and V3 are 0, we know that there is a 0 volt at the positive terminal, so there must be a 0 volt at the negative terminal, right? So what would happen is there would be a 0 here, a 0 here, a 0 here and a 0 here. So this R2 and R3 will not have any effect. They would be virtually shorted out because there is a ground at positive terminal. There is a virtual ground at the negative terminal, and we are assuming that in superposition V2 and V3 are 0, so there is a virtual ground at these two terminals. So both these terminals across R2 and R3, they will act as a short circuit while using the superposition method. So all we will be left with will be V1. So V out 1 is equal to negative RF over R1 into V1. And then coming to the second input, same. So let's remove the 1 from V out from here and let's see what happens. So V out would be equal to this plus negative RF over R2 into V2 plus negative RF over R3 into V3. So that would be expression of V out. What effectively is happening here is that V out is the inverted sum of RF over R1 into V1 plus RF over R2 into V2 plus RF over R3 into V3. So we are just adding these three voltages plus at the same time we are multiplying them with a certain gain. So these three are the gain 1, gain 2 and gain 3. And this is a very useful configuration. And by using this, what we can do is we can give an offset voltage to our input. We can shift levels and we can combine the effect of voltages coming from multiple sources and treat them independently, give them an independent gain, and then combine them at the output. And we will see their applications later on in the applications section of these operational amplifier configurations. So this configuration is the summing amplifier, but the inverted sum. Now what would happen if we do the same thing, connect multiple inputs with the non-inverting terminal and use the non-inverting configuration and try to use it as a summer? Let's try to find out. So let me draw an op-amp with a positive terminal, a negative terminal, and we can see what would happen. So the negative terminal will be grounded through a resistor, and there will be a feedback resistor connected to the output terminal, and here we are getting our V out. This is our F and this is our in. And now let's connect multiple inputs instead of a single input to the positive terminal. So this is our R1, this is our R2, this is V1 and this is V2. Previously, if you remember that the non-inverting configuration, just like here, had that input coming directly to the positive terminal of this op-amp. There was no resistor in between, and the gain was determined using the R2 and the R1 only. There was no resistor here. But in this case, in case of summing, we cannot connect two voltages to different voltages here at the same node without connecting any resistor between them, because that would result in a short circuit. So what we have to do is, when we are connecting multiple voltages at a single node, we have to do that through resistors. So here we have V1 and V2 connected to the non-inverting input of our amplifier. So previously our calculation was fairly simple, because we assumed that whatever Vin is coming at this point should come at this point also. But now we don't know what Vin is coming at this positive terminal, because now there is not just one Vin connected, there are two Vins connected. What would be the effective voltage here? Let's solve it using superposition again. So first, let's assume that to find the V plus, let's assume that V2 is equal to 0, just like we did in the non-inverting case. Now when V2 is equal to 0, what would be the value at V plus? V plus would be equal to R2 over R1 plus R2 into V1. How? Let's redraw this circuit. This is our V1, this is our R1 and R2, this is our R1, V1, and this is our R2, and from this point we are getting the V plus, and this V2 is equal to 0 for now. So what is the value of V plus? We can find it here, R2 over R1 plus R2 into V1 using the simple potential divider rule. So this, let's say this is V plus 1, and what will be the value of V plus 2 due to this second input voltage? That would be equal to R1 over R1 plus R2 into V2. And now our calculations become fairly simple. We know the value of V plus that is coming on the positive terminal because of these inputs, though independently, but we can solve it independently, and then using superposition we can add the output voltages. So let's find out. V out 1 is equal to, this V out 1 is due to the V plus that is coming due to the effect of V1 here. So that would be equal to R2 over R1 plus R2 into V1, and then multiply it with the gain. And what was the gain? 1 plus RF, this one, over R in for the non-inverting input. So that is fairly simple. What we had to do was, we just had to find out what was the V plus coming at this positive terminal, and then use that one as the input voltage to the op amp itself and multiply it with the gain of a non-inverting amplifier. And similarly, our V out 2 would be equal to, just like we derived, R1 over R1 plus R2 into V2, again multiplied by the gain, that is same in this case also, 1 over 1 plus RF over R in. And then what would be the value of final V out for the summing amplifier, non-inverting summing amplifier? V out would be equal to V out 1 plus V out 2, just like we do in superposition. So just add these two values and you will get your V out. So you have to be very careful while doing these kind of calculations, because if you see here, the mistake that the students do because of the lack of practice is, while finding the V positive 2, they will do R2 over R1 plus R2. But as I have drawn this circuit here, that explains very clearly that for the V1, R2 should be in the numerator because of the voltage divider output. So this is just a potential divider, and the potential we are getting because of V1 at the V positive, the positive terminal of this operational amplifier, is the voltage drop across the R2, not the R1. And similarly, in case of V2, the voltage drop is across the R1, not the R2. So you have to be very careful in solving these kinds of circuits. So far we have discussed the unity gain buffer, the voltage follower, that was the basic of a feedback based operational amplifier configuration. And then we moved on to a little bit more complex inverting amplifier configuration, where we selected the gain of our own choice. And then we moved on to the non-inverting amplifier, where the input was not inverted by phase. And then we have discussed a summing amplifier, where there were more than one inputs. So there can be 2 or more inputs, and we can solve for that. All those inputs were applied at the single terminal of the operational amplifier. That single terminal can be positive terminal or that can be negative terminal, and those multiple voltage inputs were supplied to that terminal through resistors, through the input resistors. But we have not supplied the inputs to both the inverting and non-inverting terminals at the same time. So what I am going to do right now is, I am going to use multiple inputs, not just 2 inputs, 3 inputs, let's for that sake, and I'll try to solve those circuits for both inverting and non-inverting summing amplifiers. That what would be the case if there are more than 2 inputs. For a single input, we just use the voltage divider configuration and superposition, and that's it. That is very simple. But what would happen in case of 3 resistors, 3 input resistors? What would be the circuit and how to solve that? So first, we'll do that. And then after solving that and understanding that, what we are going to do is we are going to use inputs at both the terminals at the same time. Inputs will not be provided on just one terminal. So let's start with 3 inputs supplied at a single terminal. The inverting amplifier has already been covered. So what happens in case of non-inverting amplifier with more than 2 inputs and using it as a summing amplifier? So this is your V out, this is ground, RI and RF, and here we have 1, just a second, let me move it a bit to the right. This is 1, 2 and 3 inputs, all connected to the non-inverting input of this amplifier through these resistors R1, R2 and R3. We already solved it for 2 inputs. Here you can see that R1 and R2. We already did it. What would happen in case of 3 inputs or more inputs? Again we'll use superposition, but in this case we have to be very careful. For example, for the effect of V1, V2 is equal to V3 is equal to 0. Let's assume that. And when V2 is equal to V3 is equal to 0, this circuit becomes here, here. So this is your V1 and not Vi. This is your V1. This is your R1. This is your R2 and R3. And this is your V2 and this is your V3. But they are both equal to 0 now. So this will be your final circuit. And the V plus 1, the voltage at the positive terminal of this operational amplifier, due to the effect of V1, the input V1 would be equal to what? The voltage drop across this point, right? So this is your Vi plus. And what is that? That is R2 parallel to R3, we can see that, divided by R1 plus R2 parallel to R3 into V1. And now that you have the V plus 1, things are fairly simple. What all you have to do is you find the V out due to the Vi plus 1, and then you find the V out due to the Vi plus 2, and then due to the Vi plus 3, and then just add them. So what would be the final expression of V out? So let's try V out 1. V out 1 is equal to R2 parallel to R3 over R1 plus R2 parallel to R3 into V1 and into now this gain RF over RI 1 plus RF over RI. So this is your V out 1. V out 2 would be equal to R1 parallel to R3 over R2 plus R1 parallel to R3 and so on so forth, and then V out would be equal to V out 1 plus V out 2 plus V out 3. That is very easy, but that is a bit tricky. All you have to do is you have to be very careful what actual voltage, what actual potential is present at this terminal and at this terminal. Solve it using superposition method by assuming all the other input voltages as 0 and then add the effect of V out of each individual V in, and then you will get the final result. So that's it for the multiple inputs for a summing amplifier for both inverting and non-inverting configurations. And next up we will be discussing the differential amplifier or the difference amplifier, and in that configuration, as I said earlier, that the input voltages, there will be more than one input voltages, but those will not be applied to the same single terminal using the input resistors, but those will be applied to the two terminals separately. Both of these terminals will have an input rather than one of the terminals being grounded. Like in this case, the negative input terminal is grounded. In this case, the positive input terminal is grounded. And in this case again, the negative input is grounded, and the voltage inputs are supplied only at one of those two terminals. But in the next one, we'll be finding out what would happen if we apply input voltages to both the terminals, not just one of those two terminals. Alright, so now, as we have discussed the inverting and non-inverting amplifiers and the weighted sum of different voltages, multiple voltages using the inverting and non-inverting amplifiers, let's move on to the difference amplifier, where you have multiple inputs, more than one inputs, effectively two inputs, but those two inputs are not supplied to the same terminal of the operational amplifier. Rather, one input is applied to the inverting input and the second input is applied to the non-inverting input of the operational amplifier. Let me draw the circuit diagram of a differential amplifier, or a difference amplifier as you call it. So this is a symbol of operational amplifier, and here we have the two inputs. We will supply our first input to the inverting terminal using a resistor, and we will supply our second input to the non-inverting terminal through a resistor, and we will ground the positive input using a second resistor. So let's call this resistor R2, this is R1, this is R3, and this is R4, and this is our V out. If you see here, we are applying V1 at the non-inverting input and V2 at the non-inverting input. So again, we will be using the superposition principle to find out the relationship between our V outs and our V ins. So our V out 1 will be due to the effect of our V1, and that is simply a single voltage input V1 coming at the inverting input terminal, and the op amp will act as an inverting op amp. So we can simply write the transfer function of this as negative R2 over R1 into Vi1. Now for the non-inverting amplifier, we have R4, R3 through which our V2 is supplied, and we have R2 and R1 as our feedback resistors. So now one very important concept here is that while we are using the superposition method, what we do is we assume that only the input we are concerned about, and we are calculating our V out for which input is there and is applied at the input terminals, but all the rest supply voltages are 0, and V1 is one of those supply voltages. So if I just replace this V1 with a ground terminal, it will be nothing more but a simple non-inverting amplifier. So what is the transfer function of a non-inverting amplifier? V out 2 is equal to 1 plus R2 over R1 into V plus. Now what is that V plus? If you see here that V plus is equal to R4 over R3 plus R4 into V2, this is nothing more but a simple potential divider. So we can write simply R4 over R3 plus R4 into V2. And now that we have V out 1 and V out 2, our final V out would be equal to V out 1 plus V out 2. and that is equal to negative R2 over R1 into V1 plus 1 plus R2 over R1 into R4 over R3 plus R4 into V2. This is a difference amplifier, but we cannot see it yet. We know that our one input V1 is coming here at the output with a negative sign, as we can see here, and our second input V2 is coming here with a positive sign. So this means that something is happening, and some gain into V2 minus some gain into V1 is happening. But if the gain was equal, that would be equal to G into V2 minus V1. If this G for V1 and G for V2 were equal, only then we can have a difference and give us same gain to that difference. Otherwise, it would be equal to G2 V2 minus G1 V1. Now G2 is negative R2 over R1, and G1 is 1 plus R2 over R1 into R4 over R3 plus R4. What would happen if I make G1 is equal to G2? What do we need? We want these two gains to be equal, and how they will become equal is very simple. R2 over R1 should be equal to 1 plus R2 over R1 into R4 over R3 plus R4. To make these two equal, what we can do is we can put R4 over R3 equal to R2 over R1. It is just like replacing this R4 with R2 and this R3 with R1. And now let's rearrange this equation and this expression and see what happens. So R2 over R1 is equal to 1 plus R2 over R1 into here R4 over R3, multiply and divide by R3, R3 over R3 plus R4 over R3. I have just multiplied and divided it with the R3, so no effect. And now replace this R4 over R3 with R2 over R1. So 1 plus R2 over R1 into R2 over R1 over 1 plus R2 over R1. And you can see where it is going. The denominator here, in the denominator we have 1 plus R2 over R1, and here in the numerator we have 1 plus R2 over R1, so they'll just cancel out. And what will be left is R2 over R1 is equal to R2 over R1. So effectively we can have a gain of R2 over R1 into V2 minus V1 if our R4 over R3 is equal to R2 over R1, or you can say R4 is equal to R2 and R3 is equal to R1. Even if this second condition is not fulfilled and only the ratios are equal and their actual values differ, like R4 is not equal to R2, R4 is 10 R2, but R3 should also be equal to 10 R1. And that would make it a difference amplifier, that is amplifying the difference of two voltages. That is why it is called a difference or differential amplifier, where the gain is same for both the inputs and the inputs are being subtracted from each other. What is the use of this? Usually we have two types of voltage inputs, two sources of voltage inputs. In one source, our voltage is coming with reference to ground. But in many cases, our voltage is not coming with reference to ground. We are getting a differential voltage input. For example, in case of a bridge circuit. In case of a potential divider, if you can see here, this is a potential divider. So the V out here is with reference to ground. So we have a single-ended input that is already with reference to ground. But in case of a bridge circuit, we are getting the difference of VA and VB. And we want to amplify this difference. We don't want to give a separate gain to VA and a separate gain to VB. So otherwise this difference will be affected. We are interested in the VA minus VB. So for instance, the VA minus VB in a bridge circuit that was del V was changing from 0 to 20 millivolts. And that was with respect to the change in resistance R3. We want to amplify this del V. We don't want to amplify VA separately and VB separately. It is a differential input, it is not a single-ended input. And that's why this difference amplifier or a differential amplifier is really very important, because we can directly take a differential input at its input terminals. Now, what is the disadvantage of this particular configuration? There are many disadvantages. The first one we can see here is that this V1 is not directly connected to this negative terminal. Similarly, this V2 is not directly connected with this positive terminal. So this configuration, again, not this amplifier, this amplifier configuration will act as a load on the supply input. This amplifier, though, have an infinite impedance, but this particular configuration where our input is not directly coming at the negative terminal or positive terminal of the amplifier, this means that this is now a system. This is not an independent operational amplifier, and this system does not have an infinite input impedance. Its input impedance as seen by V1 would be R1 and as seen by V2 would be R3, because they are coming at the input of this system. So if you are connecting two stages of or two systems together, the input impedance of the second stage will act as a load at the first stage. And the second disadvantage of this configuration is that the effect of loading should affect V1 in a similar way and in an absolutely equal magnitude as it is affecting the V2. So it is absolutely necessary that this R1, the input impedance seen by V1, is equal to the input impedance seen by V2, and that is R3. So we have to exactly match this R1 and R3 to make the effect of loading absolutely equal on V1 and V2. What if the effect of loading was not equal on these two inputs? Same would happen. This gain would be different for these two voltages. So our difference would not be amplified. V1 would be attenuated by a different level and V2 would be attenuated by a different level, resulting in an error in our output that we don't want. And similarly, if our R1 and R3 are absolutely equal, and to keep the gain, this gain R4 over R3 and R2 over R1, the ratio, that to keep that equal, we have to absolutely and perfectly match R2 and R4. So the next question is how to change the gain if we want to tune the gain. Like if in case of an inverting and non-inverting amplifier, we can see here that the expression says the gain will change if any of these inputs change. So just by changing this one resistor, this RF, the feedback resistor, we can tune the gain. But what about this? In this case, the gain will change if either of R2 or R1 changes. But if we see carefully, there is now not just one R2. There are two R2s, because this has to be R2 and this separate independent resistor, this component, should also be R2. And similarly, there are two R1s. So to change the gain, we have to adjust both R1, both R1s or both R2s. We have two separate physical resistors that we have to change absolutely equally. Now just tell me, if you have two potentiostats whose resistance varies between 0 to 10 kilo ohms, how many of you can change both the resistors together and absolutely adjust both of them on 5.053 kilo ohms? I think not more than 1 in 10,000 persons can do that. So changing the gain of this differential amplifier is not an easy task. Rather, it is really very difficult. You cannot have a varying gain amplifier, differential amplifier, if you use this configuration. You have to do something about that, because if you want a varying gain, just like a volume control knob in your musical instruments, you cannot have a single knob. You have to adjust two knobs at a time simultaneously and make sure both of them are absolutely at the equal value. Otherwise, your output is going to have some error. So these are the two disadvantages. What is the third disadvantage? That we will discuss when we will be discussing the common mode input and common mode rejection. So we'll come back to that. So for now, just keep in mind that there are two major limitations associated with this particular configuration. Now coming to the first limitation, and what is the solution? The first limitation was the effect of loading here, that this R1 and this R3 act as a load on the differential input voltages V1 and V2, and we just discussed in our previous sections that how op-amps themselves can be used to eliminate the effect of loading. There was one configuration, one most basic first configuration that we discussed for this purpose, this particular purpose, and that was the unity gain buffer, the voltage follower. And at that time we said, okay, it is not giving any gain to the input voltage, so what is the purpose of op-amp? Now you can see what is the purpose of that op-amp. That op-amp can be connected at the between these inputs and this differential amplifier configuration and can eliminate the effect of loading, just like this. Let me draw that circuit. So we have one input coming here, one feedback, and here is our operational amplifier. So this is our output, V out, R2, R1, and then again this is our R1, and at the non-inverting terminal this is our R2. So what if we connect two unity gain buffers or voltage followers at the inputs of this differential amplifier and provide our inputs V1 and V2 here? What's happening now? This is a unity gain buffer, and this V1 is now supplied directly to the positive terminal of this unity gain buffer. Hence, it is directly connected to an infinite input impedance device, that is this operational amplifier directly, and same goes for this V2. So there is no effect of loading on either of V1 or V2. Then here we have again V1 and V2, because this is a unity gain buffer, so these voltages will just pass through but without the effect of loading. And as this operational amplifier has a zero output impedance, so as far as the current supply is inside the limitations of the maximum current supplying capabilities of this operational amplifier, this will keep supplying V1 and V2 without any loading effect to this R1 and this R1. There will be no effect of loading because the output impedance of this amplifier now is 0. No effect of loading. So one problem solved. What about the second problem? Change both R's simultaneously or change both R2's simultaneously to change the gain. What we can do about that? There is a special configuration called an instrumentation amplifier for that particular purpose. And in that particular configuration, what we are going to do is we are going to derive the expression of some gain into V2 minus V1, and that gain would depend upon R1, R2, R3, R4 and Rg. So if there are pairs of resistors R1 and R3 and pairs of resistors R4 and R2, there is a single resistor Rg, that is the gain resistor, and that is just one entity, one physical component in that circuit, and changing that Rg can change the gain. We are going to derive that soon. Before coming to that, I would like to give you some concepts of what is a differential input, what is a common mode input, and what is common mode rejection, and what are the problems associated with that. So let's first discuss the common mode problems, and then we'll move on to the instrumentation amplifier to tackle these issues. Alright then. So before starting the operational amplifier, let me go through some basic concepts of differential input and common mode input. An op-amp, that is a 3-terminal device, has two inputs, one positive and one negative, and there is one output. And in the differential amplifier, we just saw that we can configure this operational amplifier to get a gain of R2 over R1 into V plus minus V minus. So the difference of these two voltages is amplified with a gain that is set by setting the ratio of R2 and R1. This difference, V positive minus V negative, is called the differential input voltage, V diff. There is another type of input that we call as common mode input, and that is the sum of these two voltages divided by 2, or you can say the average of the input voltages, and that is called the VCM, V common mode. So if we rearrange these equations and put one equation into the other, we can get V1 or V positive is equal to VCM minus V diff over 2. In case of differential amplifier, if we use this formula of V out, we can write that R2 over R1 into V diff is equal to V out. And when the difference between the positive and negative inputs is equal to 0, V out should be equal to 0. If both of them are 0, again, then the difference would obviously be 0 and V out would be 0. But the point to note here is that if the difference between these two outputs, these two inputs is 0, but these two inputs themselves are non-zero, like this is 2 volts and this is 2 volts, their difference would be 0, but these inputs individually will not be equal to 0. And in that case, we'll get an issue of common mode input. What happens is, when there is a common mode input, we will see that if V plus is equal to V minus, V diff will be equal to 0, but V common mode will not be equal to 0. 2 minus 2 is 0, 2 plus 2 over 2 is 2. So there will be a common mode input, and that common mode input will not be equal to 0. And ideally, what should have happened was that our output should have been absolutely 0 if our difference of the inputs was 0, but that doesn't happen. So let's see how and why. We can write V1 is equal to VCM minus V diff over 2, and V2 is equal to VCM plus V diff over 2. just rearranging the upper two equations. Then the gain, the formula of gain in which our R4 over R3 was not equal to R2 over R1. This was the formula that we derived for the output voltage of a differential operational amplifier configuration. So this means that V out is equal to negative R2 over R1 into V1 plus 1 plus R2 over R1 into R4 over R3 plus R4 into V2. So let's just put the values of V1 and V2 in this formula and see what happens. Let me rewrite that formula here for you. V out is equal to negative R2 over R1 into V1 plus 1 plus R2 over R1 into R4 over R4 plus R3 into V2. Replacing V1 with this and V2 with this, we'll get V out is equal to negative R2 over R1 into VCM plus R2 over 2R1 into VDiff plus 1 plus R2 over R1 into R4 over R4 plus R3 into VCM plus 1 plus R2 over R1 into R4 over R4 plus R3 into VDiff over 2. And taking VCM and VDiff common, we'll have V out is equal to VCM into R2 over R1, negative R2 over R1 plus 1 plus R2 over R1 into R4 over R4 plus R3 plus VDiff into R2 over 2R1 plus 1 plus R2 over R1 into R4 over R4 plus R3 into 1 over 2. So now we have our output written in terms of VCM, that is the common mode input, and VDiff, that is the differential input. So there are two types of inputs that are now present at the inputs of our differential amplifier. So what I can write here is that I can break this equation into two, and I can write V out over VCM is equal to ACM, the output voltage due to the common mode input divided by the common mode input is equal to the gain, the common mode gain of this differential amplifier, and that is equal to this quantity right here, negative R2 over R1 plus 1 plus R2 over R1 into R4 over R4 plus R3. And again I can write V out over VDiff, the output voltage because of the differential input over the differential input is equal to A diff, the differential input gain, and that is equal to this quantity right here, and that would be equal to R2 over 2R1 plus 1 plus R2 over R1 into R4 over R4 plus R3 into 1 over 2. So this is your differential input gain. Now, what is the significance and what is the meaning of these two equations? Ideally, there should be no ACM. The common mode gain should be 0 because we don't care whether there is a common mode input or not. Why? Because we are interested in amplification of the differential input, not the common mode input. What we want to do, what we want this configuration, this differential amplifier to do is that the difference of the two inputs should be amplified, and if the difference is 0, regardless of whether both the inputs were individually 0 or not, if both were non-zero but their difference was 0, we want a 0 output. Eliminating this common mode gain and making it nearest to 0 is called common mode rejection. And the common mode rejection ratio is the CMRR. The common mode rejection ratio is the ratio of a diff over a CM. That is the ratio of your differential gain, that is the desired gain, and your common mode gain, that is the undesired gain. And you can see here that this ratio should be very large value. This ratio should be a very large value, because we want our actual gain, our desired gain, that is the differential gain, to be much greater than the undesired gain, that is the common mode gain. And this is the common mode rejection ratio. What is the CMR? That is the common mode rejection coefficient, that is equal to 20 log 10 of CMRR. Now the typical values of CMR range between 60 dB to 100 dB. These are the typical values for a good amplifier. How to reduce it? How to make our amplifier closest to the desired ideal value? And that is by putting that condition R2 over R1 is equal to R4 over R3. So this is your golden rule, using which you can make your ACM as close to 0 as possible. In reality, what happens is that it is impossible to 100% match these two ratios. There would always be an error. Even if you used fixed resistors, those resistors have certain tolerance. R2, R1, R4, R3, these are 4 individual components, and all those 4 individual components will have some tolerance and will have some manufacturing error, the range between which those values would vary. For example, if I have a 1K R2 and a 100 ohm R1, the ratio should be 10, but that 1 kilo ohm would not be precisely 1000 ohms. For a 5% error, it can range between 950 ohms to 1050 ohms. So there would be an error of 50 ohms here for a 5% error. For a 1% error, that would be 990 ohms to 1010 ohms, and so on so forth for all these 4 resistors. 1% error is very much acceptable in resistors, and it should be kept in mind, because a resistor of 1% error is considered to be a very good resistor. So even if we use really good quality resistors, we'll have around 0.5 to 1% error in these values. So it is impossible to perfectly match these two ratios. But what if they are 100% absolutely matched? The ACM will go to 0, because the gain ACM, the formula for that is negative R2 over R1 plus 1 plus R2 over R1 into R4 over R4 plus R3. And if we multiply and divide it by R3, divide by R3, this term would become R4 over R3 over 1 plus R4 over R3. So this means that this denominator R1 plus R4 over R3 would be cancelled with this 1 plus R2 over R1 if R4 over R3 is equal to R2 over R1. And the only remaining thing would be R4 over R3 that is equal. So the ACM would be equal to minus R2 over R1 plus R2 over R1, and that is equal to 0. These resistors can almost never be very well matched, and there will always be a common mode gain. Now when you are going to buy some amplifiers, some ready-made amplifiers from the market off the shelf, there can be just the op amp, or there can be a complete configuration of the op amp that is miniaturized inside that IC. So you can get an IC of just this operational amplifier without any external components, without any resistors or anything. And you can also get a chip that has all this circuit built in there. A differential amplifier, you can buy an off-the-shelf instrumentation amplifier, and so on. And the price of those instrumentation and differential amplifier ranges between 70-80 rupees to almost 1700 to 1800 rupees, even more than that. So then what is the difference between these two? The cheaper one has more tolerances and has a higher ACM that was undesired because the resistances were not well matched, because the silicon process that was used to fabricate that chip was not that accurate. In the other case, in the more expensive IC, the silicon process was really refined. Very strict quality assurance standards were met, and it was made sure that those resistances were well matched. Apart from that, there are some other things that are present in the higher end instrumentation amplifiers or amplifier configurations as compared to the lower end. What are those? Those are the input voltage offset. What is the input voltage offset? The input voltage offset is when you have a single-ended input and you get an output but with an offset. So you have to offset your input to adjust that offset in your output. That offset in your output is undesired. You are getting a gain, you are getting the required value, but with an undesired offset. So that undesired offset is manually corrected by providing an offset at the input stage, because you cannot change the output. The output is produced by the op amp. You can only change your inputs. So you change your inputs intentionally, manually, introduce an offset at the input stage, and that reflects as a compensation of the offset, the undesired offset that was present in the output stage. So that offset is almost not present in the higher end op amp configurations. The second thing is the slew rate. The slew rate is related to the response time of the operational amplifier. Its definition and its formula is given in your book. You can study that. Then the third thing is the voltage characteristics and the current characteristics. The basic voltage characteristics of an op amp include the range of supply voltage, the range of input voltage, and the mode of supply and input voltages. Some amplifiers cannot take a supply voltage that is both positive and negative. They can only take a positive with a ground, and similarly their inputs are can be given only with reference to ground. There is no negative side. Rather most of the amplifiers have dual level supply. Both positive and negative voltages can be given at both the supply and the inputs. Another feature of op amp supply voltage is rail to rail. What is rail to rail? If you have an operational amplifier and its supply voltage changes from 15 to minus 15, the rail to rail input and rail-to-rail output are two separate terms. In case of rail-to-rail input, your input can range between your actual SPI values, minus 15 to 15. It can be less than that, but it can be maximum your SPI voltage, your input. Same goes for your output, that your output will swing between your actual SPI levels. Most of the operational amplifiers, the cheaper operational amplifiers, do not have either rail-to-rail input or rail-to-rail output. For example, if your op-amp was powered up with plus 15 and minus 15 volts as the SPI voltages, you can only take inputs from minus 12 to plus 12, and similarly your output can only swing between negative 12 to plus 12. So there is a difference of plus 3 and minus 3 volts between your SPI voltages and your inputs and outputs. So this is not rail to rail. This circuit in blue is not rail to rail. Another thing about these is the current handling capacity. Mostly there is no current flowing through the inputs to or from the inputs, but in reality the input impedances are not infinite. We know that they are very, very high values. They range from 50 mega ohms, 10 mega ohms to hundreds or thousands of mega ohms. So in the lower end operational amplifiers, you have lower input resistances or impedances that are not desirable, but in the higher end amplifiers you have very high input impedances that is close to the ideal, and that results in very low offset currents. That offset current flows in your into or from your inputs, and that shouldn't happen. So your higher end operational amplifiers solve this problem. And again, your current handling capacity or the current supplying capacity of the operational amplifier is also one factor. Your cheaper or lower end operational amplifiers usually have a maximum I out of around 1 milliampere, while or maybe 0.1 milliampere, but your higher end same category op amps have a maximum I out of 10 milliamperes, 10 times that of the cheaper. But mind it that this is for the same category of microcontrollers. There of operational amplifiers. There are hundreds of categories of operational amplifiers, and you can see that you can get even 200 milliampere I out in case of a 30 rupees op amp IC. So it doesn't mean that this explanation is wrong. This means that the IC in same category that costs 300 rupees would have even higher I out, and that would be equal to around 300 milliamperes. So we have to see in which category that op amps belong. So now we know that why it is really very important to keep this ratio, this R4 over R3 equal to the R2 over R1 to reduce that common mode input and the common mode gain that is not desired. And as I said earlier, as I was deriving the differential amplifier's transfer function, we discussed that if this ratio, these two quantities are not equal, one end of the of this input will be given a separate gain and the second end would be given a separate gain. So that gain would not be same for both the input voltages, and we will eventually not be able to say that the difference was amplified. We can say that one input was independently amplified and the second input was independently amplified, and that is what gives rise to this ACM. this was the basic formula. So V1 was being amplified by R2 over R1, while V2 was being amplified by this whole expression. So even if V1 was 2 volts and V2 was 2 volts and R4 over R3 was not equal to R2 over R1, this V1, let's say this gain was 2 and this gain was 2.5. So ideally this output should be equal to 0 because we want V2 minus V1 to be amplified. But what's happening here is we will get 1 volt output. Even if these two are equal and V2 minus V1, even effectively that was equal to 0 volts. How? Let's see here that here was your bridge circuit and your VA that was equal to 2 volts and your VB that was equal to 2 volts. So what should be the V out here? That should be equal to 0 volts. And now your bridge null is disturbed because of an inaccuracy of this operational amplifier or a differential amplifier. So we have to be really very careful about this. Now move on to the instrumentation amplifier, and we discussed the limitations of a differential amplifier. So let's see which of those limitations are solved using an instrumentation amplifier. The basic form of instrumentation amplifier was discussed earlier. Here in this diagram we just included two voltage buffers at the inputs that solved the loading effect of the differential amplifier, but this problem of R2 over R1 and R2 over R1 to change the gain remained the same, and that is what happens. The major issue arises when this R4 over R3 and R2 over R1 have to be some physical external resistors that can never be as accurate as on-chip fabricated resistors. If your physical resistors have a tolerance of plus minus 1%, your on-chip fabricated resistors may have tolerances up to plus minus 0.1%. These are the physical components and these are the on-chip resistors. So what we would like to do is we want to fix and fabricate these 4 resistors on chip. But what problem it gives rise to? The gain would be fixed, because in this configuration you can see that the gain would be fixed. If we fix the value of these resistors and we use very accurate resistors, we cannot change the gain. So our amplifier is useless, because in every other application we must have the liberty to choose the gain ourselves. And if we use very accurate resistors and use the on-chip fabricated resistors, we lost the opportunity to adjust the gain. And that issue is addressed using the instrumentation amplifier, where we fabricate these 4 resistors on chip, but we leave an opportunity of one variable resistor to be connected externally outside the circuit, and that just one resistor would be able to adjust the gain of this differential or instrumentation amplifier. And now let me draw that instrumentation amplifier schematic, and we'll see what happens. And from the negative end we want a feedback of one resistor, and again from here we want a feedback here, and then in these 2 points we have an RG, and here at the positive terminals we are getting our inputs. So this is V1 and this is V2, and here we have a feedback at the second stage and a ground resistor at the input of the second stage, and this is our V out. So now this is our R4, R3, R3, R4. So now what I'm saying is I'm calling that R2 and R1 both has R4 and R3, not R2 and R1. So this stage, this second stage, is nothing else but a simple differential amplifier. And then this one, this RG, is a single resistor that has no pairing element in this circuit, and these two resistors, these are R2 and R2, and you can call this RG as R1. So this is R1 equal to RG. So right, the first thing we can notice in this configuration is that these inputs are directly connected to the positive terminals of our op amps. So there is no effect of input impedance of this configuration. The second thing we can notice here is that this R4, there are two R4s. So this is a pair. Then there are two R3s. Again, this is a pair. And there are two R2s. So this is also a pair. So these, when I write R2 on one resistor and R2 on the second resistor as well, this means that these two separate individual physical components must be exactly, absolutely matched to reduce the common mode voltage. But we can see here that fortunately we have this one resistor RG or R1 that doesn't have any twin element in this circuit, and the V out is equal to R4 over R3 into 1 plus 2R2 over R1 into V diff. Assuming that these resistors are absolutely matched, the gain of this stage, this second stage, we already know that the A diff was equal to R4 over R3 in ideal cases. And what is this? If I check, if I try to analyze these two circuits individually, the upper stage is a non-inverting amplifier and the lower stage is a non-inverting amplifier. The only difference is that by the way, the gain of a non-inverting amplifier is 1 plus R2 over R1, right? We already know that. So the only difference in this configuration, this upper half, and the non-inverting amplifier is that this second resistor, this R1, is now not connected to the ground, but it is connected to the negative input of the second input stage. And after derivation, we find out that this gain of a non-inverting amplifier becomes 1 plus 2R2 or R1. Each of these become like this. So this is the gain of the first stage and this is the gain of the second stage. So your V out is only dependent on the V diff, as we can safely assume that these R4, R3 and R2 are matched exactly in pairs. Why? Because now all of them, the green portion, this green portion is inside the IC, and these resistors are fabricated on chip with very high accuracy, and this variable resistor is outside. So whatever the value of this R1 is, it will just define the gain. So that is your instrumentation amplifier, and it fairly rejects the common mode noise, and the ACM is approximately equal to 0. It has a very high common mode rejection and signal to noise ratio. Up to this point, the various configurations of operational amplifiers, the basic configurations of operational amplifiers, in which we can just take inputs and amplify them or add them or subtract them, are completed. But the next thing we are going to discuss is some other configurations, like using the op amp as an integrator or a differentiator or a voltage source or a current source, or